Amazing. Hi, everyone. Today I'll be talking about our latest work, Iris-MSWasm, a program logic for memory-safe WebAssembly. This work is at the confluence of three broader topics: the WebAssembly language, the use of capabilities as a strategy for accessing memory, and the iris separation logic. So let me walk through how we got there in the middle to Iris-MSWasm. The starting point for me has been the iris separation logic, which is a framework to reason about separation logic. The idea is that you can instantiate it with any programming language that you'd like, as long as you're able to describe the operational semantics. What Iris gives you back is a set of proof rules you can use to reason about the behavior of programs written in your logic. And what's really brilliant is that it has an implementation in Coq, so you can do formal analysis with a theorem prover of language, the behavior of programs written in your own programming language. And this has been used to do a number of different things, but mostly with simplified languages where you put a spotlight on a specific feature that you'd like to study. And what we wondered is, are we able to make this scale up all the way to an industrial style language? And the language that we have identified as the best target for this usage was WebAssembly, as we found that it strikes a very good balance of being both something that people widely use and care about, but still having a full formal specification, which makes it relatively easier to do formal analysis on compared to other languages where even defining the operational semantics in Coq would be a challenge. The specificity of WebAssembly that we've focused on is that code is exported in modules, and WebAssembly guaranteed what's called state encapsulation, meaning that a module is not supposed to be able to arbitrarily meddle with another module state, say its memory, unless specific objects have been explicitly exported. And we wondered if we'd be able to formalize this using Iris as a universal contract, and that's how a couple of years ago we introduced Iris-Wasm, an instantiation of Iris with the full WebAssembly language. So that means we now have a program logic that can be used to reason about the behavior of WebAssembly code, but we also introduced a logical relation that can be used to reason about unknown code. Say, if I have a library function to a library that I don't know or maybe trust, I'm still able to say meaningful things about the behavior of that code, and that's what we call robust safety, when I reason about code that I know nothing about. The universal contract we captured there was local state encapsulation, meaning we finally formally enunciated and proved that property of WebAssembly. That probably most people already knew WebAssembly has, but it's neat to have a formal proof. But more interestingly, this is a very good starting point now to start reasoning about variations of WebAssembly. So where do capabilities come in? One limitation of WebAssembly is that the memory safety guarantees are inherently very coarse-grained. What I mean by that is the level of granularity WebAssembly has is the module. So if I'm a module and I have a memory, if I'd like someone else to have access to a specific part of my memory, I have to share everything. And in specific use cases, you might want to have the ability to share at a finer grain. You might want to be able to share specific parts of your memory, but not the entire thing. Retain authority over some parts of the memory that contain maybe secrets that you don't want to share with unknown code. And one way, of course, to obtain finer grain safety is to use capabilities. Now, a capability can mean a lot of different things. For the sake of this talk, a capability can be thought of as a pointer together with some meta information that defines the authority that that capability has. So that could be, say, a range of memory that I'm supposed to have access to. A couple of years ago, Alexandra Michael and her co-authors introduced MSWasm, memory-safe WebAssembly, which is a variation of WebAssembly where we would use capabilities instead of pointers to access memory. The types of capabilities used in MSWasm are called handles, and they're these records with 5 fields. You have a base and a bound that define the range of memory you're meant to have access to, an offset that defines where your handle points to, and then valid and ID, which are 2 other fields that are used for performing dynamic checks when you load and store. The way now it works to load and store from memory using a capability is that whenever you read or write, we're going to dynamically check that you are accessing a region that you're supposed to be allowed to access. So the rule for loading, called segment loading in this instance, is the one I'm displaying here. The last premise is what you'd expect from a load rule. I go into segment memory at the address specified by my handle. I read object C, and that's what I reduce to. All of the other premises are these dynamic checks. I'm verifying that I'm within the range that I'm supposed to be allowed to access. I'm verifying that the validity bit is set to true. I check that with using my handle's ID, I am still live. I have not yet been freed. And if all of those things are true, then I'm allowed to perform my segment load. Otherwise, I reduce to a trap instruction. That means that something has gone wrong, but no memory violation has occurred yet. We thought this was a brilliant work, but we wondered if we can do better than the pen and paper proposal that has been done, both to provide more assurance and confidence in the properties that you get from memory-safe WebAssembly, but also because the definition of memory safety introduced by Michael and et al. Was a little bit difficult to understand, difficult to use in practice, and we thought we could introduce an even stronger property using Iris. Now, Iris has been used before with WebAssembly. That's what I talked about earlier. There was Iris-Wasm. Iris has also been used to reason about capabilities. There's a number of works I could cite here. Probably the biggest one would be Cerise. And we wondered if we could adapt these ideas to get there in the middle and formalize MSWasm. And I'd like to stress here that even though my Venn diagram might suggest it's as easy as just overlapping two already existing concepts, it's very, very difficult to actually make these works work in the case of an actual language that has all of the specificities of true languages. But when you massage everything together, you get there in the middle and you get Iris-MSWasm. So what we've introduced in this paper is a formalization of the full MSWasm system, including the model system in Coq, and that in itself has been incredibly valuable as it has highlighted a small number of typos in the original work, as well as a number of places where it was imprecise or incomplete. We now have a program logic that can be used to reason about code written in memory-safe WebAssembly, as well as a logical relation to reason about unknown code. So again, robust safety in memory-safe WebAssembly. And this time the universal contract that we have shown is robust capability safety, which is a much stronger property than what we had before. It basically means we have finer grain safety. And now with the remainder of the time I'll get a little bit more technical about how exactly you can use Iris-MSWasm and how exactly we got to this product. So let's look at a very simple program that illustrates how Iris-MSWasm might be used. I'm importing an adversary function fadv that I know nothing about. That could be a library function from a library I don't know or trust. I'm now allocating two handles, two spaces in memory, h and h prime, writing a value, secret value 42 to my first handle h, and then I call my adversary function with argument h prime. And now what I wish to have is when I return from that call, if I read the value and place it in a global variable, that's still the value 42 that I'd written there. This is a really interesting example because I want some form of sharing. I'd like the adversary to have access to h prime. I cannot just say I'm going to wall off all of my states. I want some form of sharing, but I still want to retain authority over that h prime zone of memory. The whole triple in separation logic that I'd like to show is displayed here in gray. So if I have a resource corresponding to that g variable to begin with, no matter what value it points to, I would like at the end either to still have that global variable resource now pointing to 42, or I have trapped, meaning something bad has happened. What could that be? Allocation could have failed, because in our model we model realistic machine behavior where allocation may non-deterministically fail. Or my adversary call might have had some undefined behavior in it, division by 0, or a number of other behaviors that might have caused that trap. But importantly, if a trap occurs, it happens before any memory violation has occurred, and we consider that to be safe, which is why it's allowed there in our postcondition. Now, if you've done separation logic before, you might have some intuition of how you might go about proving this. Here are the intermediate steps. When I allocate my two handles, well, that could trap, so I have a trap that I place already there on my second gray line. But if it does work, then I get two extra resources corresponding to my handles h and h prime. When I do that write operation to h, I modify my resource. Now I know that it points to 42. Then there's the interesting line. The most important and difficult one is the call to the adversary. And I'll say a little more on the next slide about that. But if you can trust me that I can get to that next line, then it's easy to conclude. When I read from H, I just inspect that resource corresponding to those areas in memory. I set my global variable G by simply modifying my G resource, and I end up with the triple I wanted. Now, how do I reason about this call to fadv that I know nothing about? That's, again, a robust safety property. One way to obtain this is to define a logical relation. And if I give a very, very high-level overview of what that means, I would like to define what it means for a program to be safe to execute. I'll note that with this double turnstile as opposed to the single turnstile used in syntactic typing in the WebAssembly's type system. And what I'd like is to define this very carefully so that I get the fundamental theorem for the logical relation, which is that if I type check in my program's syntactic typing system, then I am safe to execute. Sometimes being safe to execute is called type checking semantically. So in that case, the fundamental theorem becomes if I type check syntactically, then I type check semantically. Now, in separation logic, being safe to execute can be defined using this weakest precondition construct. So I can define a program of type T1 to T2 to be safe to execute if, whenever I give it an input value that is safe to use for type T1, I have this weakest precondition statement, which means that my program plugged with that input value V is going to be running safely, and if it terminates on a value W, such that W is safe to use for type T2. Now, of course, I'm hiding everything behind the definition of being safe to use. What it now means is going to depend on the type of my value. If I am an integer, we can just say that all integers are safe to use. But for a handle to be safe to use, I would like to be able to perform loads and stores to it. So I'm going to define a handle to be safe to use whenever either it's invalid, meaning it's going to fail my dynamic checks and not trigger any memory violations, or I own the memory resources corresponding to that specific handle. And importantly, only those resources. I do not need to own other parts of memory. I don't need to own the entire memory, only the bytes that my specific handle has authority over. Small caveat, I might be able to read some handles, so I need to recursively ensure that any handle that is stored at that location recursively is safe to use for the handle type. And last caveat, trap is always safe, so I have to add it into my set at the very end. Obviously, this is massively oversimplified. In the case of an actual language like WebAssembly, what I'm accessing is not object, it's a raw array of uninterpreted bytes, so I have to take into account that different types will be deserialized with different mechanisms. I have to take address alignment issues into concern. MSWasm also has a very specific way of freeing handles, so I have to keep track of that as well. But if all of this is defined very carefully, I'm able to prove the fundamental theorem by induction on my syntactic statement. And that's what I mean when I say universal statement, universal contract. When I do this proof, I would like every single instruction in my language to verify that as long as something is safe before, it will be safe once it reduces. And now with this fundamental theorem, I have imported function fadv. WebAssembly's import system guarantees that anything that has been imported has at one point been type checked at instantiation. So I know for free that that code type checks syntactically. Using the fundamental theorem, I now know that it type checks semantically, meaning as long as I'm able to provide it with an input that is safe to use, and I am able to do that because I have memory resources for h prime, I will be able to run my function, and if it terminates, all of the values are still safe to use, so h prime is either invalid or I still have this resource, but that doesn't matter because I don't need h prime anymore. And importantly, I did not need to yield my resources g or h. I was able to stick to them, and that's how I'm able to finish my proof over here. So to conclude, Iris-MSWasm has formally verified and validated the pen and paper proposal for memory-safe WebAssembly, and finally given a formal, precise statement of what this memory safety means and proved it in a proof assistant. By doing so, we've used a number of novel techniques that will be interesting to use when doing future work with separation logic on real-world languages. More generally, this is an illustration, if we still needed one, that machine checks proofs are possible even on industrial scale languages, and we'd love to see more work using theorem provers to do things with real world languages as well as and not just simplified examples. Iris, I think we've illustrated, is a very good tool to do that, and specifically in the case of WebAssembly, we think Iris-WasM is a very good starting point when trying to formalize new versions or extensions of WebAssembly with new features. So as futures works, our team as well as other teams from different universities are already looking into leveraging Iris-WasM for other variations of WebAssembly. There are 2 examples here on the slide, but there's certainly more that can be done. Thank you very much.
Questions?
Very nice work, thank you. I just wonder with the WASM GC proposal, like they would get like something like low-level memory safety if you would still like probably go to higher level capabilities. Have you thought about that?
I have not had a look at that at all, no, sorry.
Thank you.
More questions?
Thanks. Yeah, again, really interesting work and I think really important problems. I do actually have a question which is, just to make sure I've understood what you were saying. You said you're making a call out to that function about which you know nothing, but then I think you also said you do know that that function is type checked within WASM.
Yes, that's the way WebAssembly performs instantiation. If I want to import a function from a different module, I don't, instantiation will guarantee at runtime that everything type checks. Otherwise, the import is not going to be made available for my other module. That's just the way the WebAssembly instantiation mechanism works. So I do have that guarantee that if it's imported from a different WebAssembly module, that has gone through the WebAssembly instantiation.
Right, okay, but so it's type checked at the WebAssembly level, it's not type checked at the Iris level?
No, it's type checked at the WebAssembly level, in the very simple WebAssembly type system, yes.
And so how do you know that that code doesn't already have a side channel access to whichever H it is that you're protecting?
So you'd have to trust that the implementation you have of MSWasm verifies the specification. All of the work we've done is on the specification level, so I guess in practice you'd need to make sure that your implementation verifies the operational semantics as is defined in
Right. So if I don't know, I'm going to try and say something backwards and see if you think I'm right. Is it because you have checked your code with WASM and you know that you have the ownership of both H1 and H2?
So one aspect of handles is that they're unforgeable. So if the adversary has never been given access to one of these handles, it should not be able to forge one and to
the separation logic tells you that you know that the adversary hasn't got it because you've got all of it.
That is correct. The separation logic is reflects the fact that as long as you're not been able to have a hold of a handle, you're not able to just make it appear. You have to be either the person who's allocated that handle, or you have to have been given the handle or a subset of it from someone who has.
Right. And what's important that you're able to do that without actually requiring any proof on the external code.
Isn't it the case? Sorry. Isn't it the case that for the adversary code, because it's well typed, you know it's in the logical relation, and that gives you certain guarantees? That's relevant to this.
Yes, that is correct as well. I'm not sure.
Sorry, I was saying that isn't it the case that the adversary code, because it type checks, and all syntactically well-typed code is semantically well-typed in the logical relation, that tells you certain things about the adversary code, which perhaps are the things that you're asking about?
I guess the issue is whether you require only the semantics of WASM to do that, or whether you also require a separate proof in Iris-MSWasm of the external code.
So the only contact the Iris-MSWasm has with that external code is the application of the fundamental theorem. From the fact that I know that it type checks syntactically, I get that weakest precondition statement without needing to yield any resources corresponding to handles that I am not providing for that code as an input.
Right.
was going to ask a quick question about new separation logics. Can you say something quickly about that?
About new separation logic.
New separation logic techniques or something. You have something in the future that this yields insights that would be useful.
Yes, and I mentioned it very quickly when I said that this is very oversimplified. This is a presentation of what a logical relation for pointers looks like in a textbook scenario. And some of the parts that I wasn't able to show were specifically memory alignments and deserialization concerns that were difficult to reason about. And that required a very complicated definition with a lot of existentials on exactly which parts of the memory I actually have resources to. And I'd love to talk more about it offline if you'd like.